Well, welcome to Module 1, Earth and Sun Systems. I'm Tom Weichel, and this is my office. And this is where I'm going to be making the videos for this course, Physical Geography, Geography 1114. So it's great to have you here. Sit back, relax, and we'll get going. This first video addresses the size and shape of the Earth. So we're going to sort of start by taking a look back and sort of zoom out, if you will, and talk about the origins of our solar system. And to do that, it's necessary to at least say something about what formed our solar system and the galaxy that our solar system is located in. So about 14 billion years ago, scientists believed there was a tremendous explosion that took place with materials that were sent off in every direction. And that's called the Big Bang. Part of the Big Bang theory, and this is sort of an artist's conception of what the Big Bang might have looked like. We know that, among other things, the Big Bang formed a number of galaxies. Included in the list of galaxies is the one where our Sun and solar system are located, and that's called the Milky Way galaxy. So we're going to take a look just for a moment at the Milky Way galaxy. The Milky Way forms a big spiral. So sort of this image kind of represents what it might look like if you were viewing it from above, whatever that means. It's sort of a relative term, above or below. But you can see the location. That orange dot shows the approximate placement of our Sun and solar system in the Milky Way galaxy. So part of Orion's arm. The lower part of this diagram represents sort of a cutaway, if you will, a profile view of the galaxy. And it gives you some idea of how tremendously large the Milky Way galaxy is, and it's one of many galaxies. The Milky Way galaxy is believed to be 100,000 light years in diameter. So what does that mean? Well, a light year is the distance that light travels in 1 year. So we know that light travels about 186,000 miles per second. So that's a pretty considerable distance. It's just really hard to get your arms around that. So to talk about some of the other objects in our Milky Way galaxy, I thought it might be helpful to present this little subunit. I call this "Do you feel small?" And I feel small when I consider how big some of the objects are that are in our galaxy and other galaxies. So let's take a look at sort of a sample of stars that are in our galaxy. And we're going to start with Antares. Antares is a massive star. It's a red supergiant that has a surface temperature of around 6,100 degrees. It's nearing the end of its life, so that astronomers believe that it's going to collapse into a supernova at some point and explode. So let's take a look at the size of Antares. So what I've done is I've superimposed this line right here, which shows you the approximate location of planets, or at least some of the planets in our solar system, if they were superimposed over the center of Antares. So at the center here of this line is a dot and an S, and that refers to the location of the Sun. And then the approximate location of Mercury is shown with the M. The V is Venus, E is Earth, and M is Mars, and then J is Jupiter. So this is a really big star. I mean, it's just massive. It extends all the way from where the Sun would be located all the way out into an asteroid belt, which is nearly to the planet Jupiter. So this is a pretty big star. So let's just take a look at, for fun, a couple of others. Betelgeuse is a red supergiant that's located about 725 light years from Earth. So that's still a pretty big star. Let's take a look at just a couple of others for comparison. Aldebaran. This star's name comes from the Arabic word for follower. It has a surface temperature of around 6,700 degrees, and it's only 65 light years from Earth. So smaller than the other stars, but a whole lot closer. A really bright star is Rigel. Rigel is named for the Arabic word, the left leg of the giant, and it's considered a blue supergiant. And it has a surface temperature of around 36,000 degrees Fahrenheit, so a whole lot hotter than these other stars. And then one that is a little bit smaller than Rigel, going back to this one's a giant, considered just a red giant, not a supergiant, but it's located pretty close to Earth, about 36 light years away from Earth. This star, Arcturus, is believed to be around 7 billion years old. All right, moving on. Sirius, also sharing the name with the satellite radio broadcasting service, is believed to be about twice the mass of Earth, but it's 25 times brighter than the Earth's sun. In fact, it's the brightest star in the night sky, and it's located pretty close to the Earth, only about 8.6 light years from Earth. All right, let's go ahead and compare Arcturus and Sirius to the size of the sun. So there's the Earth's sun in comparison. So you can see why the sun probably wouldn't have even shown up on the previous slide. It's so small, but it's still pretty big. And we're going to compare the sun in the next slide here to the other planets in our solar system. So there at the center of this image is the planet Jupiter. So it's the largest planet in our solar system, superimposed to scale over the sun. And you can see the Earth is really just kind of a dot. The Earth is really pretty small. And in fact, if you compare the Earth to the sun, and we used a penny to represent the size of the Earth, it would take 109 pennies, or the diameter of 109 Earths, to span the diameter of the sun. So that's pretty remarkable. So the sun is even though a whole lot smaller than some of the other stars, it's really pretty big compared to the Earth. And here's a view of the Earth in relationship to Jupiter. And in fact, that big oval there that's right behind the Earth, obviously this isn't the location of the Earth, but that big thing that's on the surface of Jupiter is a storm that's been going on for a long time. As long as we've been taking pictures of Jupiter, this storm has existed in the atmosphere of Jupiter. But that's kind of a relative image of the Earth compared to Jupiter in terms of size. Well, what about our solar system? When did that form? Well, it's believed to have formed around 4.6 billion years ago as materials began to coalesce into the planets. I'll talk a little bit about the 8 planets, and you might think, okay, wait, 8 planets, we're leaving out one. What about Pluto? Well, we'll talk a little bit about that, and if Pluto is a real planet. All right, let's take a look at this image. This image has some issues because it sort of misrepresents the size of the planets relative to each other. It's really useful for sort of showing the order of planets, beginning with Mercury, and the location of the asteroid belt that's there between the orbits of Mars and Jupiter. So let's talk a little bit about and sort of focus on the Earth for a little while, and at least the planets that are closest to the sun. So this is what the Earth might have looked like when it was first forming. It was made up of a lot of molten rock that began to cool, and the surface of the Earth, no one was there. No one really knows exactly the way it might have looked, but this is sort of an artist's conception of, volcanoes and a lot of molten material that was there as the Earth began to cool and form into something that had a hard crust. So let's go ahead and take a look at some of the planets that are closest to the Earth, and we're going to sort of throw the planets into sort of under 2 categories. And the terrestrial planets, also called the inner planets, are those planets that are closest to the sun, and they are Mercury, Venus, the Earth, and Mars. So how are these planets different from planets that are a little bit farther away, like Jupiter and Neptune? Well, the terrestrial planets, or the inner planets, are more spherical in shape. So if you look at and measure their shape, they're closer to a ball, a perfect sphere. Although they're not a perfect sphere, and we'll sort of talk about why that is. They're also hard in their composition, and I'll talk a little bit about how that's different from some of the outer planets in just a moment. They also tend to have a slower rotation than some of the other planets, some of the planets that are located a little bit farther away. So again, more spherical in shape with hard materials that make them up, and typically slower rotations. And here's sort of a cutaway of one of the terrestrial planets. We're looking here at Mars, and we have a solid core, and then we have the mantle, which is made up of kind of a liquid rock that's or magma-like rock that's still cooling, still in a hot stage, and then a hard crust that we call the crust. So that's one cutaway of a terrestrial planet. Let's take a look at the difference between the terrestrial planets and the Jovian planets. So the Jovian, or outer planets, include Jupiter, our biggest planet, Saturn, Uranus, and Neptune. in order. So how are they different? Well, once again, they're more, I guess you could say, you could call them more oblate in shape. They actually bulge at their equator. So the equator is that location halfway between the pole, say the North Pole of Jupiter and the South Pole. The equator is right in the center, and these planets actually bulge a little bit because of centrifugal forces. So they're not as perfectly spherical or round compared to the inner planets. The Jovian planets are largely made up of frozen gases, and they tend to spin at a faster rate. So we'll get to that a little bit later, probably in another video. And if you do a cutaway, take a look at a cutaway of the Jovian planets, here we have Jupiter, which is largely made up of frozen methane, nitrogen, and frozen carbon dioxide with a solid rock core. And that's kind of strange to think that they're not made up of those same types of hard materials that make up the Earth. Here's a view of the 8 planets. Again, we're kind of leaving Pluto out of the list, shown approximately to scale. And I think it does a pretty good job, again, sort of representing how big the Earth is relative to Jupiter. Now, what about Pluto? Well, Pluto sort of left off the list because scientists have discovered a number of dwarf planets. And among the dwarf planets that they've discovered that are very similar to Pluto is this one called Eris, abbreviated UB313. And it has an orbit that's different from Pluto, but it has many of the same characteristics as Pluto. It's a very small planet. Let's sort of look at at a comparison of sizes and orbits. Here's the Earth, and here's the size of the Moon relative to the Earth. And Pluto and Eris are very similar in size, but Eris's orbit extends way out, much farther, a much larger orbit than Pluto. So the thinking is, well, if you've got these dwarf planets, are they really truly similar to the other 8 planets? So there's this new category of dwarf planets. Okay, what about temperatures of the planets? I think it's useful to sort of compare the temperatures of planets in Fahrenheit, kind of see how they stack up relative to each other. And as you might expect, a planet like UB313 that's located pretty far away from the sun is going to be pretty cold. Here we have a temperature of negative 400 degrees. It's the estimated temperature on Eris. And as you get closer to the sun, the temperatures go up. And so our average temperature here on Earth is, say, around 68 degrees. But what about Venus and Mercury? What seems sort of a little bit odd about the temperatures of those 2 planets? So think about that just for a minute. You would expect to find Mercury actually being hotter than Venus because it's closer to the sun, but it's not. Venus is actually actually hotter than Mercury. So how could that be? Well, if you think about it, it has something to do with the fact that Venus has an atmosphere and Mercury doesn't. Venus has an atmosphere that's made largely of carbon dioxide, whereas Mercury has no atmosphere. So some of the radiation, some of that solar energy that's absorbed by Venus is actually retained by its atmosphere in something that we call the greenhouse effect gone wild. So it's retained in a similar way to the carbon dioxide in the Earth's atmosphere holding on to energy. So more about that a little bit later when we talk about energy received by the Earth. So let's move on. Let's talk a little bit about what holds these planets in place. So why do they stay in these orbits? Well, it's sort of tied back to Newton's law of gravitation. And I'll let you read Newton's law. I won't read it to you here on the screen, but basically what Newton's law says is that every single object in the universe has a force where it's attracted to every other object. And what determines the amount of force or gravity or attraction is the size of each object and how far apart they are, very simply put. So how big each object is and how the distance between them. So let's take a look at Newton's law of gravitation in an equation. And I'm not going to throw a lot of equations at you this semester. This is one of a very small number of equations. But let's take a look at this equation just for a minute. And what we've got is F, which refers to force, equals a constant times the mass of one object times the mass of the second object divided by the distance squared. So let's try to apply that to something we know. So let's take the Earth And let's take the International Space Station, or really any satellite that's in orbit around the Earth. So we've got the M1, or the massive object 1 would be the Earth. M2 would be, let's say it's the International Space Station. And if we look at the distance between them and apply that idea to this equation, we can get some idea of the gravitational attraction between the two. Now, let's try to apply this idea to something you're familiar with. If you've been to a coastal area, what causes tides to go up and down? Think about it. Why do the tides go up and down? Well, one thing that we know that drives tides is the heavenly body, the moon. We know that the moon has a gravitational attraction on the ocean, and it pulls on the ocean. So it helps to push and cause tides to move in the direction of the moon when the moon is sort of facing that place on the Earth. But another object in the universe also has a major effect on tides, and that's the sun. So we know that if you're in a coastal area and the tides are really high, that's because the Earth and sun are lined up. So we'll look at that a little bit later. But that's something you can actually see in a coastal area, the effect of gravity on something on the Earth. Okay, some other things that are affected by gravity. How about giant asteroids like this one? So this is an artist's conception of a huge, asteroid or meteor hitting the Earth. And there are actually some places on Earth where we can document some of the impact on the Earth's surface. So we don't see a lot of craters because we have a lot of vegetation covering the Earth, but a few places where you can still see where there's been an impact like this one in Canada. So this is a crater from the impact of a meteor that happened a long time ago, 214 million years ago. But this thing is 70 miles in diameter. That's pretty big. Here's another sort of a little video artist conception of something that happened more recently. About 45,000 years ago, a meteor struck the Earth near Flagstaff, Arizona. So this is south of the Grand Canyon. If you're ever on Interstate 40 driving past the Grand Canyon, you'll see a sign for Meteor Crater, and this is actually the visitor center that's shown here on sort of the upper right-hand part of your screen, and the location of Meteor Crater in the state of Arizona is also shown. So this is an impact place where a meteor came in contact with the Earth, and you can still sort of see evidence of that contact. So, all right, let's go ahead and turn our attention. The main topic here is the size and shape of the Earth. So how big is the Earth? Well, here's a view from space, and let's go ahead and throw some numbers that give you some idea how big the Earth is. And we're going to go ahead and compare the diameter of the Earth in two places. We're going to compare what's called the polar diameter, which would be measured from the North Pole to the South Pole, to the equatorial diameter, which would be represented along something called the equator, which is a line that's drawn all the way around the Earth, approximately halfway between the North Pole and the South Pole. So what's interesting, if you look at this image, the equatorial diameter is actually 27 miles greater than the polar diameter. So we can still call the Earth nearly a perfect sphere. It's not quite perfectly spherical in shape. We have a bulging equatorial diameter, and that was caused when the Earth was formed by centrifugal force. All right, let's move on a little bit. And just for fun, let's take a look at the highest and lowest place on Earth. Do you know where they are? Do you know the highest place on Earth and the lowest place on Earth? Well, the highest place on Earth, probably some of you guessed it, Mount Everest, 29,000 feet tall. And that's measured relative to mean sea level, what we call MSL, or mean sea level. So 29,028 feet above mean sea level. We know that is located in the mountain range called the Himalayas in Asia. And then the lowest place, maybe you might not be quite as familiar with the Mariana Trench, located about 36,000 feet deep, and that's in the Pacific Ocean. So that's our highest and lowest places on Earth. So just for fun to consider, the sort of some variation in the Earth's surface. So how about the tallest mountain on Earth? Do you know what the tallest mountain on Earth is? Well, it must not be Everest, right? Because we just talked about Everest. That would be the easy answer, to say it's Everest. So if you measure from the bottom of the mountain to the top of the mountain, what would be the tallest mountain on Earth? Well, it's actually located in the U.S. That's your hint. It's not in Alaska. That might be your first. You might be tempted to say it's Denali Peak or Mount McKinley in Alaska, but that wouldn't be right either. It's actually Mauna Kea. Mauna Kea is the highest point on the big island in Hawaii. So this is the big island of Hawaii right here where I'm pointing, if you can see. And there's Mauna Kea in the center top of that slide. And you can see the observatories up on top of Mauna Kea. And if you measure from the bottom of the ocean floor, or the bottom of the mountain, to the top of Mauna Kea, it's about 6.3 miles. From the bottom or the base of Everest to the top of Everest is about 5.5 miles. So here in the US, we have the tallest mountain on Earth. So we can be pretty proud of that, I suppose. All right, we'll go ahead and finish up there, and we'll move on to the next video in a moment.